Hi, my name is Blake Forland, and I'm a graduate student here at Indiana University in the physics department. My research is in high-energy particle physics, and specifically I'm searching for particle collisions that contain two Higgs bosons. Now, to get a complete idea of the story of fundamental particle physics research, we should really begin at the beginning with the Greeks in 500 BCE. However, I've been told we don't have enough time for that, so how about this? If you've ever opened your phone with your thumb or your face, you've inadvertently interacted with a piece of technology that plays a large role in my research: image recognition. Image recognition is a part of a much broader concept known as machine learning. Quickly and simply, machine learning is when a researcher exposes a computer to a particular task, and through repetition, that computer becomes an expert at that task. One example of this is we could train a computer to tell the difference between cats and dogs by showing it pictures of cats and dogs and having it guess which is which. And critically, if we correct it when it's wrong, over time the machine would learn to tell the difference between the two. This is known as supervised machine learning and plays a large role in my research. And actually, the phone in your pocket has another piece of technology that is a direct analogy to how I carry out my particle physics research, and that's the camera. I use data from the Atlas detector, which is an incredibly large and complex machine, but we can think of it as just a very large camera. Now, when I say large, I mean just truly huge in scale. The Atlas detector is 44 meters long, 25 meters wide. It weighs 7,000 tons. It has 100 million electronic channels, but we can think of those as essentially pixels. And so what we have here is a 100 megapixel enormous camera. The Atlas detector is one of several detectors at a research facility in Europe called CERN. You can learn more about CERN and the Atlas detector in my colleague Ashley Brooks' talk. The Large Hadron Collider at CERN collides protons together at 0.99999, really close to the speed of light. Now, these collisions, when carried out with enough energy, can produce new particles. How can these collisions produce new particles? Well, we might remember Einstein's famous equation, E equals mc squared, or energy equals mass times the speed of light squared, and this is essentially how. By colliding particles together with incredible energies, we can create more massive particles than the protons themselves. In this case, millions of times more massive. Now these particles collide and the detector takes pictures of them, and the detector takes tons of pictures. Millions of particle interactions are recorded by the Atlas detector every second. We can't keep all of these. Even a fraction of these collisions over the course of the year ends up being terabytes of data, thousands of terabytes of data. So through a truly ingenious process, these billions of collisions are filtered down to about 1,000 of events that then need to be analyzed. But this is still 1,000 of events per second, and so even for a rare process like the one I'm searching for, this ends up being millions of events that need to be examined. So the Higgs boson was observed by the Atlas and CMS collaboration in 2012, completing the picture of one of the most successful theories in physics, the standard model of particle physics. This observation led to a number of new measurements, such as the mass of the Higgs and its interactions with other particles. This interaction with those other particles is intrinsically related to the origin of mass itself. Now, the standard model also predicts that the Higgs boson is capable of interacting with itself, and one way that this can be observed is through the simultaneous production of two Higgs bosons. To do this, we create information that describes the collision, momentum of the particles, orientation, and their mass, and use this information to come up with a description of the event that can be used to identify a particular event, such as an event that contains two Higgs bosons. These so-called di-Higgs events are incredibly rare, and for this reason we use machine learning to identify these events amongst millions of other events which we're not interested in. This machine learning allows us to teach a computer how to identify these events, but often the computer can make connections in the data that aren't obvious at first, leading to a tool based on machine learning that is quite successful at accomplishing its task. The algorithm we've created to carry out this search depends a large part on image recognition. It's designed to identify particle collision events that contain two Higgs bosons based on this image. Probably not what you were expecting, but it's worth remembering that we're talking about subatomic particles. There's no way to image them in any way that we might be used to. Without going into too much detail, this image here tells us something about the spatial separation and physical separation of the two decay products of a single Higgs boson. And those characteristics are unique to di-Higgs events. So we trained a computer to look at this image and tell the difference between it and other events that we're not looking for. Through the supervised training process, we've created an algorithm that is incredibly successful at identifying di-Higgs events. But why? Once completed, our analysis will tell us more about the nature of simultaneous Higgs production, as well as tell future analyses how sensitive they need to be to this process in order to observe it. Outside of physics, it can be hard to relay the importance of fundamental physics research because the applications are often not immediate. Even with direct application being difficult or delayed, we find benefits of the research while it's being done. Throughout its history, CERN and the research that is being carried out there has been responsible for many technologies that have had profound impact on our lives. The World Wide Web was developed at CERN. We've spearheaded state-of-the-art machine learning and data storage. The Atlas Collaboration has a global network of computers for its research that is made up of tens of thousands of machines. The Collider itself has spearheaded cryogenic applications throughout the Collider ring, and so much more. Often it's not what's discovered, but it's what's developed along the way towards those discoveries that have such profound impacts on our lives. I'm implementing state-of-the-art machine learning technologies that will not only have impacts on particle physics, but as the field of machine learning progresses, it could have impacts elsewhere. Even more profound isn't the measurement that tests the standard model, but it actually has implications for the stability of the universe that we live in. But one thing at a time.